Today we're going to discuss one of the three major theorems for our class that you need to be prepared, that you need to understand, to apply, and to recognize when a situation is calling on it to be the reason. So today we're going to discuss the mean value theorem, and for short we'll call it MVT. Now the proof of the theorem is beyond the scope of this course, but we can understand the theorem in a relatively simple way. So one thing to notice is that it's called the mean value theorem, and mean also means average. So somehow this is related to an average. Now, the conditions necessary for the mean value theorem to apply: one, you need to be on a closed interval. That means we're including endpoints. And two, a function must be continuous on this interval. So under these two conditions, a closed interval and a continuous function on this closed interval, the mean value theorem applies. And finally, the third feature is that the function must be differentiable on the open interval. What I mean by that is excluding the endpoints, the function must be differentiable everywhere in between the two endpoints. So graphically, to contrast the two situations a bit, we could have one graph, and we'll just focus on the first quadrant for sake of ease, which starts at some x value we'll call A, and ends at some x value B. Let's say it has a shape something like this. So here we have a closed interval, right? The interval is from A to B. The function is continuous, that means there's no open spots on that entire interval. And on the open interval from A to B, I could take the derivative anywhere. There's no sharp points or corners or cusps. If we were to contrast this with maybe, here's a familiar graph, the absolute value graph, y equals the absolute value of x, and if we focused from, say, -2 to 2, this would be a situation where the mean value theorem does not apply. And this does not apply because it doesn't meet the third condition. This function is not differentiable at x equals 0. Right, so the mean value theorem does not apply in that particular case. Another example graphically of where the mean value theorem would not apply: if you have a function, again we'll use from A to B, and somewhere there's an open interval. Again, in this case, the mean value theorem does not apply because it's not continuous on the entire interval, right? There's a breakdown right here. So we've got one example graphically of when the mean value theorem applies, and two where it does not apply. One because it's not differentiable, the other because it's not continuous. Right. The similar way, let me give a fourth example. If we're talking about something and we're going to focus between A and B, but we're not including the endpoint A. Well, here the mean value theorem does not apply because it's not a closed interval. We're not including A, we happen to be including B. So again, it does not apply. So let's talk about what the mean value theorem is, now that we've got at least established when it applies and a few examples of when it would not apply. So imagine, if you will, we have some function, again we'll say in the first quadrant just for sake of ease, and it's on a closed interval from a to b, and it starts here, whatever that a value is, we'll just say that that's f of a, because it really doesn't matter what it is. And it has this kind of a shape and increases up to f of b. And there are two things that are true about this graph amongst lots of things. One is that the secant line going from A, I'll do it in red, the secant line going from A to B has a slope. Right, and its slope would be f of b minus f of a all over b minus a. Right, and all that is the slope of the secant. Now, something to make sure you have clear in your head is that this is also called the average rate of change. And it's the average rate of change because we took the total amount of change, f of b minus f of a, and divided it by b minus a, which a way to think about that would be the total time it took to go from f of a to f of b. And that would be an average. The total change divided by the total time would be the average rate of change. Right, so the slope of the secant is also known as, or a way to think about it, is the average rate of change. And that's going to be an important connection that you have clear, that anytime you think of average rate of change, you're thinking about slope of a secant line. Right, make sure you have straight in your head why that would be an average rate of change. Now, the other thing that's true, and I'll do this part in blue, is that there is a tangent line somewhere on this interval from A to B. It looks like it might be about here, that is parallel to our secant line. Right, so our tangent line, the slope of our tangent line, will be parallel to, or our tangent line will be parallel to our secant line, so the slope of the tangent line would be equal to the slope of the secant line. And that's going to happen at some point, and we'll say that point is C, where C is somewhere between A and B. And so the slope of our tangent line is equal to the derivative of our function at the point C. The mean value theorem relates the slope of that secant line to the slope of the tangent line, or more specifically, the average rate of change to the instantaneous rate of change. What is the rate at which the function is changing at a specific moment in time? Right? Because those two lines would be parallel, their slopes would be the same, which means, since their slopes are simply the average rate of change and the instantaneous rate of change, they will be equal, those two rates. So the mean value theorem says that under our given conditions, on a closed interval, where a function is continuous and differentiable on the open interval, there is at least one point right, if those conditions are met, at least one point on the interval points on the open interval, because that's where it's differentiable, a to b, the slope of the secant will equal the slope of the tangent, or, in terms of calculus, the average rate of change, which is the slope of the secant line, will equal the instantaneous rate of change. Right? Or at some point, if you want to think about it in terms of velocity, the average velocity will equal the instantaneous velocity. It could be at more than one point, but it must occur at least one point. Let's consider maybe another graph that might illustrate this a bit, and we'll think about it graphically at first. So again, we'll focus on the first quadrant, but the quadrant is not the issue. We could have a graph that starts at A and goes to B, and it happens to look something like this. It goes to a maximum, heads back down to a minimum, goes back to whatever f of b is. And the slope of our secant line would be related to this line in red. And our tangent line would have the exact same slope, perhaps at some point like here. They'd be parallel, so their slopes would be the same. And perhaps at this point here, those lines would be parallel and have the same slope. The mean value theorem guarantees that there's at least one point where that must occur. And there could be more than one, but we know it must happen at least one point. We'll look at a few more examples of this in the next part.